schematic up. Okay. Let me get the slideshow from current slide. And now why I need to back up one. Oh. Okay. No, I didn't need to back up one from current slide. Okay. The last, I guess, 3 announcements they are. My office hours today are normal. And fortunately, on Wednesday, they'll be normal, as far as I know, okay? Don't know of anything that's going to interfere with office hours today or Wednesday, okay? Which are the days we meet, okay? However, the rest of the days are really messed up. Tomorrow, I've got a doctor's appointment. It's my hematologist who only sees patients on Tuesday mornings. I tried to schedule it for spring break week, but he was going to be out of town spring break week too, so I couldn't do that, so it's coming up tomorrow. 11 o'clock, but even though the appointment's at 11, my blood work, I have to have that done by 10, which means I have to leave campus by 9:15 in order to get there, get parked, and be ready in the lab by 10 o'clock. So, that won't affect office hours but normally on Tuesdays and Thursdays they're 10:45 until 1:15. But since my doctor's appointment is 11, there's a real good chance I won't be out of his office until around 12 or so. And that means it's then another 45 minutes back here. If traffic's bad, that would be 12:45. Now, I hope I'll be here before 12:45, but, you know, it won't be a long time before that. So my office hours, rather than being 10:45 to 1:15, are going to be like 12:45 to 1:15. As little as a half hour, maybe up to an hour or so. That would be about the max. So that's tomorrow. Wednesday, like I said, office hours haven't changed. They're going to be the same. Okay. Thursday, however, is Honors and Awards Day. And I've got to check on my emails because I had a student telling me that the program started at 9, and a faculty member told me, no, we have to be there by 9. And depending on what time that is, that'll affect how much of my morning class I'll meet, but that doesn't pertain to you any. What does pertain is my office hours. Normally on Thursdays, like I said, 10:45 to 1:15, but if this starts at 9:30, which I think is what it does, then I imagine it's going to go pretty close to 11:30, which means I'll be probably 12:15 getting back to, 12 o'clock getting back to this campus, because it's on the Birmingham campus. So therefore, my office hours are probably only going to be like 12 to 1:15.
So what is your usual office hour for Wednesday?
Is basically 3:15 until 5:15, right after this class, yeah.
And Tuesday also the same?
Tuesday and Thursday are usually 10:45 till 1:15, but tomorrow it's going to be like 12:45 to 1:15, and Thursday more like 12 o'clock to 1:15. Monday and Wednesdays are the same as today, 3:15 to 5:15. Now I have a little window of office hours, like 45 minutes to 12, between 11:15 and 12, so you can come see me then. And I have another really small window between 1:40 and 2, right before this class, in between the 2 classes. Yeah. But other than that, that's all I got on Monday and Wednesday. The biggest chunk is 3:15 to 5:15. Okay, here I don't even have my book open. Any questions on differential equations?
On the test.
This is the second test?
Yes, sir.
Okay.
Where you classify.
Okay.
On the blanks, there's all the words are up there that go into the blanks, right? You don't want first order. You don't want.
What? Yes, sir.
All the.
Yeah, but what did you say I didn't want?
Like first order, anything like that.
Okay.
Basically, any word that's not up there.
Yeah, I believe that's right, because the order's pretty straightforward. I've just got to find it here. Is this your first question, or is this the fourth question?
Fourth.
Fourth, okay, that's what I thought. Okay. I want to make sure I was looking at the right test. Okay. Yeah. just, separable, exact, linear, homogeneous, or Bernoulli. So choose one or more of the five. And I tried to do the blanks to match what the key said, but if you give me a correct combination that is different, you still only have to do as many as blanks as you see. If you do come up with an extra one that is correct, you'll get a bonus for it. I don't know how precise the key was, but I tried to follow that. Okay. Good question. Any others? Were there others? Nope. Okay. All right, where my memory is that we left off was on page 130, and this was sort of incredible. 4.2 is basically 3 pages long, just about. So we should finish this today and move on to 4.3. We had done example 1, and what we were ready to do was the general case. Suppose we divide A2, which is the second coefficient function, I think I would call it. Okay, if we're looking at second order partial differential equation, second order ordinary differential equations, the A2 of x would be the coefficient function for the second order derivative. Okay, so if we divide A2 to put equation 1 into standard form, in other words, divide everything by A2. Okay, so let's go back and just get. Here's the standard form that we've been talking about. Ooh. Oh yeah, I may do that. I mean, I don't know if I want y'all to see this or not. Y'all should have good imaginations and understand what I'm thinking. Okay. Haven't you run into that in math classes before? Don't answer that. Okay. A sub 2 x y double prime plus a sub 1 x y prime plus a sub 0 of x y is equal to 0. Okay, this is the, in some sense, is the homogeneous case. It is homogeneous linear second order differential equation. Okay. Now, from back the last chapter, pretty sure it was, if not, it was the chapter before that, what we would do was divide everything on both sides by a sub 2 of x, a sub 2 of x, a sub 2 of x, a sub 2 of x. Now, of course, that last one's still 0. This one goes out completely. Now we have y double prime plus some new function, okay? And what they called it, and what we called it back earlier, was p of x. So in other words, our p of x is a1 of x divided by a2 of x times y prime plus, and then we called this one q of x. Y, and q of x was a0 of x from before divided by a2 of x from before, and this was equal to 0. Now this looks just like what we used to call, in fact, last chapter, when y'all are classifying them, your linear case, right? The standard linear form, where p of x and q of x are continuous on some interval I. So p of x and q of x continuous on I. Now, if you think about this, if indeed this a2 of x was there and wasn't just 1 to begin with, but was some function of x, now if it was just a number like 7 or 4/3 or minus 3/2 or something like that, dividing by it didn't do much at all, But if it was a function of x, like it indicated it could be, then you're dividing by a function of x, okay? Now, if any of those x's made to produce a 0 in that denominator, then these would not be continuous if that 0 was included in the interval, because then you would have a discontinuity there. You can't divide by 0, okay? So that means that any place where this a2 of x was 0, that has to be excluded. You have to pick an interval that excludes any of those. And Nigel's here. Okay. Just missing Jonathan, but we're missing him this morning too, so hopefully he'll come in. He what?
He's going to be here Wednesday when his test. He had mercy.
Oh, I'm sorry. Okay. Okay, and then we haven't heard much from Antonisha or Charles. Look forward to hearing from them soon, but we'll see. I can't remember if I sent them the second test or not. I think I did, but it's so crazy. Okay. So let's suppose further that y1 of x is a known solution to this thing. So we know this y1 of x is a solution. Okay? Now, on this interval, and that y1 of x is not equal to 0 for every x on that interval. So in other words, it's not the trivial solution on that interval. If we define this ay, such that it is some u of x times y1 of x, okay, then it follows that this y prime is equal to, you tell me, if y is u of x times y1 of x, what would y prime be? U of x y1 prime of x, first half of the product rule, plus u prime of x, y1 of x. All right, good. Okay, just a regular old product rule. Okay, how about y double prime of x? Running out of room. Oh, they didn't put the x, but we know it is. What would that be? U of x, y1 double prime of x. Okay, let me write it as, let's u prime of x, because otherwise I'll forget it. y1 prime of x, okay, plus, second, did you say that again? Yes, exactly, 2 of that, because you get a y prime, y1 prime, so that makes 2 of them, and the last term is u double prime of x, y1 prime of x. Okay, let's see if they got it right. Yes, they did. They wrote them in different order, but that's fine. Okay. Sometimes they wrote the u first, sometimes they wrote the y first. Yeah, I don't know. Now, if we group our terms just so, and what I'm going to do, I think I'm going to erase the top because I don't think I need that anymore. I hope not, but we'll see. If I do, I'll blame Nigel, okay, for making me erase it against my will. Okay. That'll be fair, won't it? Okay. All right. So what we're going to do is put together this expression, okay? Y double prime plus py prime, I'm leaving out some of the of x, as you understand it's a function of x, okay, plus qy, okay? That's what I want to put together, okay? Now, here's my y double prime, and what I'm going to do is pull out, remember we said y1 was a solution, right? And y1 being a solution means that y1 double prime plus p y1 prime plus q y is equal to 0, y1, right? Yeah, there's the prime. Can't see it, but it's there. Okay. Okay. Those, that means, if that's the solution, that means that works here. Okay? So, what I want to do is get that together, and we know that if we combine this part, here's your y double prime, but I want to get the parts that have y1 pieces in them, okay? So, okay, these y1 pieces there. Okay. Now, it's going to take maybe just a little bit of, a lot of space to do this, okay? All right. The y double prime is this thing down here. So what I want first are all those pieces with y1 double prime in it. And that's this one. So that u of x, y1 double prime of x, okay, plus, okay, I think that's all I want for right now, okay? Now, the rest of these will be over here, plus 2u prime of x, y1 prime of x. I don't know why this isn't writing well, okay? Plus u double prime of x, y1 prime of x. Okay. That's the rest of this. This is that part. And this is, the rest of it is here. Okay. I just put a gap in there. Okay. Plus, okay, py prime. Well, here's y prime. So this is going to be plus p u of x, y1 prime of x, right? And then we'll also put this other part over here, plus p u prime of x, y1 of x. Okay? What I did, I'm doing p times this y1. So p is times this and this. Okay? I'm putting this one with that and this one with the other. They're all one equation, but I'm just separating. Okay? Separating the pieces. And then the last thing is plus qy. Well, here's your y right here. Okay? So this is plus q u of x, y1 of x. Sorry, I didn't leave enough room. Okay. Now, what I want you to notice is, I'm going to erase some of these lines that are, ooh, I thought I was going to erase them. There. I think I'll erase these too. Okay. All right. This is, they're still writing the U. No, they're leaving off the X's. That's really, thank you very much. U times Y1 double prime plus P Y prime plus Q Y1, and this is Y1 prime, okay? Okay, plus 2Y prime, that's a U prime, okay, sorry. Yuck! Okay. Okay. To U prime, that's a U there, okay. Y1 prime plus 2. Goodness gracious, this is so terrible in the right. The pen is messing up. Plus well, I'm messing up too, so I guess I can't complain too badly. Okay. All right, let's start over. Okay. There's the 2U Y1 plus U double prime Y1 prime plus, hold on, P U prime Y1. Okay. I think I got all the terms there. Let's see. Y1 double prime, got it. Plus, they write them strangely. 2Y1 plus P Y1 times U prime equals 0. Yeah, we got them all there, I just don't have them quite the same. But I wanted you to notice this thing right here is exactly that, right? And we know that's already equal to 0, right? Okay, so then we can shorten things significantly, and that means all we've got left, I'll write it over here, is now I'm going to try to write it the way they do. Do they start out with U double prime? No, they start out with Y1. Y1 U double prime. That's that term. Plus 2Y1 plus P Y1. That is 2Y1 prime plus PY1 times U prime. Okay? And that's equal to our original thing here. Okay? I think I've written it the same way they did in the book. Okay? And that thing is equal to 0. I got to writing so long there, I forgot to put equals 0. You know, all that thing was equal to 0. It was up here, it was here, and it is down there. Okay. Okay. Now, because that middle part we already knew was equal to 0. Now, as if this wasn't bizarre enough, this implies that we must have, okay, a YU double prime plus 2Y1 prime plus PY1 times U prime equal to 0, or Now, here, they've done something else, and this is totally strange. And I'm going to need more room, so I'm going to erase some stuff. I thought I was going to erase some stuff. Since we've already used this, I don't think we need that anymore either. Okay. Let's see about that. I think we've already used that, so we're already hunky-dory there. Now, I think I'm going to hang on to that part. And I don't think we need this anymore. We've already substituted that in. Now, the way they do this, most of the time I want to ask myself, why are they doing this? They must have some ulterior motive, some plan in mind, but unfortunately they don't let you know what it is. Here's what they're going to do. Let's let, just out of the blue, W equal to U prime. And that's the part I say, okay, but why? Or where did that come from? Okay? Now, was there some reason I wanted to hang on to that? It's sort of disjointed here. So what they just said was either this thing is equal to 0. That's what they just said. Either y1 u double prime plus 2 y1 prime plus py1 times u prime is equal to 0. Or, now with this new substitution in here, with w equal u1, that would be y1 u1, u prime, because, I'm sorry, w prime, because w prime would be u double prime, right? Okay, so this is our, let's see if I can erase a little bit. Okay, w prime, okay, plus 2y1 prime plus py1 times w. Remember, that's y prime is equal to 0. So what we've just done here, whether you realize it or not, have done a reduction in derivatives, okay? And what did we call this? Reduction in order. Yeah, that's what we just did. When we did this, that took this thing down to that, okay? Drop that to w prime, drop that to w. Because we had no u's left over. The u got out up there because we focused all this with the u, but this was 0, so u had no play on us anymore, okay? Even though I kept this down here. We will need that coming back. So now we've got something that's a first order differential equation in both y1 and w, but y1 is some known thing. We don't have to solve for it. It was already known. Okay. Observe that the last equation, this one with the w, is both linear and separable. Okay? Now, by separable, notice this term has all y's in it. That has all y's. These are your w's. You can indeed separate them. And let's see if we're going to do that. All right, what we're going to do here, let's write this as y1 dw dx, okay, plus 2 dy1 dx plus p. Now, this is the bad part of leaving off the thing, that p is a function of x as well. Remember that. Y1, that's a function of x, okay, times w, which is a function of x, is equal to 0, okay? Now, okay. Now what we're going to do is multiply everything on both sides by dx. Okay? That'll wipe it out here and wipe it out here, but leave it there. So you have y1, so aggravating, dw plus 2 dy1 plus py1 w dx. That's not quite right. Let me back off a second here. Sometimes it doesn't pick up. Like right then it did not. Okay. This is a dx in here. W is equal to 0. Yuck. Okay, now, here are w's, there's our y1s, there, and the x's are there. So let's divide both terms here by w. Those go out, okay, and then the next deal is divide both everything by y1. Okay, y1s go out here, and I'm going to have to write the rest of it. This is dw over w plus 2 dy1 over y1 plus p dx, because the y1s went out there, is equal to 0. Now, I don't think I need the parentheses anymore, so I'm going to lose them, I hope. They were somewhat of a pain in the neck keeping up with. Okay. Now, if we were to integrate everything with respect to, and this is, you know, I think I forgot something here. When I multiplied, no, I didn't. I don't like the way they've done this. Here they left dw over w, which is fine. And then they did a 2 dy, or dy1, or y, they wrote it y1 prime over y1. But then they threw a dx there, even though we had canceled it out. Okay? And it doesn't quite seem fair to do. Okay? And then they had a pdx. Okay? And they set this equal to 0. So I do not like this form at all. Okay? But here's what they're doing. They're coming up with a solution. This is a log y. If you were to integrate all your terms here, okay? And now I don't know where to go. I think I'm going back up to the top. and I probably will regret it, but I just need more room. So I think we're through with this now, but we're probably not. But it's De Silva's fault. You know, she's making me do this. She made me run out of room here. So don't worry, Matt. It's going to get around to you soon. Okay. I think I'll clear all this. I hope I won't need that again. And this is all a note. And this sort of aggravates me. As I teach this a little more, I may start dropping some of these because they just get to be a pain in the neck. Okay? Okay. What they're doing when they integrate this, you get a log W. LNW, right? Okay. Plus. Now this has a 2 in front of it, so that would be a 2 ln y1. Okay? And what they do is move the equal sign here and make it a minus integral p dx. Now you see I left off the extra dx they put in there. I think that was just a typo. I don't think it's still in there. And it doesn't look like it is from what they do next. Okay? And then you have a plus c because you integrate 0 and you get some constant. Right? Okay. Okay. I'm going to do that next. This is log W plus, now, one of the principles of logarithm, a log b is the same as log of b raised to the a power. So this is log y1 squared. Move that up the top. Okay? And that's equal to this. Well, sum of the log is the log of the product. That's another principle of logarithm. Log of, and they put absolute values here, and they probably should have had them all here too. Okay. I just was being pretty sloppy. Y1 squared. Now, as long as y is a real number, y1 squared, it's got to be positive, but we'll continue it. Okay. And that's equal to minus the integral p dx. Does that answer your question? Yeah. Plus c. Okay. Now, I don't know if you remember this part of it. That looks just like, and I mean, they're really stretching here. Remember our p? The p was always, when you had it in the form that I've erased, but this form right here, when you had it in that form, okay, maybe I'm glad I didn't erase that. Let me erase this part above it because that's probably distracting. Okay, when you had that form, what did you do with the p? You made your integrating factor, which was e to the minus integral of p dx. Okay? Oh no, I'm sorry. Let's take this form. Sorry about that. I was jumping ahead. Let's get rid of the log, and how do you do that? Raise it to the e. Raise this to the e. And raise that to the e. Okay? Raise everything to e. Okay? This gets rid of this, and this gives you, and do they drop? Yeah, they drop the absolute value signs that have w y1 squared is equal to, do they put a minus in front? Seems like they've got to. No. Okay. Here's what they do. Okay, again, e to the something or another, keep the minus in there, that's the same as e to the same base. Let's see, how do you say this? Actually, what we should have done is probably not quite the way I did it. Okay. E to the minus, clean that up a little bit more, because that minus sign sticking out there. Okay, you took e to that side, you take e of this side as well, the whole side. Okay? And e of a sum is the product of the e's, right? So that's the same as e to the c, e to the minus integral p dx. Okay? And that's just some constant. C1, they call it, e to the minus integral p dx. Okay. Now, it says we solved this last equation for w. Of course, why not? In other words, divide everything by y1 squared. Okay? And that gives you what w is. Okay? I'm going to need more room. Yeah. Okay. Going to leave that alone for now. I don't think we need these anymore. Okay? I hope I don't need that. Oh, I probably do. But y'all remember it, don't you? Of course you do. If Matt doesn't, it's his fault. Okay. I hadn't told you I'd get you in there somewhere. Okay. I sure hope I remember that. Okay. All right. So this wound up being W is equal to write it out, C1 e to the minus integral p dx over y1 squared. That's what I had there. If you wipe those out, okay? But this w is u prime. So u prime, which I want to put du dx, I sure hope that's what it is. I believe it is. U is a function of x. Yeah, pretty sure that's what it is. Okay. Is equal to C1 e to the minus integral p dx over y1 squared. Okay. Write it in differential forms like this, integrate, and that gives you u is equal to C1 times this integral, the integral of e to the minus integral p dx over y1 squared plus some C2. Now where did that come? Oh, there's a dx here. Okay. There's two dx's, one with an exponent of e and one down here too. Now, where did that second one come from? When you integrate, you get a constant, and when you integrated this, it came out with a constant. We moved it over there. Okay, so that's where that C2 came from. All right, now, by choosing C1 equal 1, why would you do that? but they can. And C2 equals 0. Why not? Since you can choose anything you want to. We find from this, and this is the thing I erased, so I said I would regret, but they've written it again here, y is equal to u, y1, no, y is equal to u of x, y1 of x, okay? And we've chosen this equal 1, that equals 0, okay? So basically, we've gotten rid of our c's, huh? That was nifty, wasn't it? That you get u, which is, well, no, just leave it alone for now. U is equal to, okay. Y over y1 okay. Man, this is okay. Okay. That would imply that u of x is equal to y over y1. Okay, and they're both functions of x. Okay. So your u then becomes y is equal to, now it's over y1, but I'm going to move that to the other side, make it equal to y1, and this y actually now becomes y2. They just name it y2 so they don't confuse it. y1 as a function of x, you multiply it by the other side, times this integral, e to the minus p integral of p dx, okay, over y1 squared, okay, as a function of x, dx. Okay, it's just this thing. So now we've come up with our second y. y1 was 1. They just, suppose you do that, okay, and then they went through and introduced the u and got rid of the u much later. They introduced the w and then got rid of the w much later before they got rid of the u. So now we're back in this form, okay? It makes a good review of differentiation to verify that the function y2 of x defined in this equation here satisfies our original differential equation that we had, and that's this one right here, okay? And that y1 and y2 are linearly independent on any interval for which y1 is not 0. Yeah, do it. Have fun with it. It should be a blast. So let's use this right here. So I think I'm going to erase everything except that. So isn't this so much fun? All right, so we've done all this and come up with that as a solution. So let's get rid of all this that got us there. We'll have everything except, oh man, I think I should have kept that y1 too. I didn't do that. But I'll go back and write it down if I need it. There's our y2, we just didn't keep what y1 was. Okay, well they're going to tell us. The function y1 is equal to x squared. Okay, y1 is equal to x squared, and they're saying it is a solution to x squared y double prime minus 3xy prime plus 4y equals 0. So they say. Okay? Let's see if it's true. What would you do first? Take a derivative. She's got it. y1 prime is equal to 2x. And y1 double prime is equal to 2. Okay, so let's plug those in. X squared times 2 minus 3x times 2x plus 4. Is that equal to 0? Somehow it doesn't seem like it could be, does it? Oh, wait. If there was a 4x. Oh, 4y. I left off the y, didn't I? Yes. I left off the y. And y is x squared then. X squared. Now it will work, I think. So this will be 2x squared minus 6x squared plus 4x squared. Sure enough is equal to 0. Bingo. That is a solution. Okay? And that's true anywhere on the interval 0 to infinity. Okay? I don't think they want any negative x's in there because then that might mess up this term here. Okay? So keep the x's positive and you're okay. Okay. So that's the solution. Now find the general solution of the differential equation on the interval 0 to infinity. Using that. Well, if that's our y1, our y2 is going to be y1, which is x squared, times the integral of e to the minus integral p dx. Okay, we've got to figure out what a p is. Over our y1 squared, well, y1 was x squared, so y1 squared would be x to the 4th, right? And that's times dx. Okay. Now, all we've got to do is go back and say, wait a minute, what is our p? Okay? Well, where did we get our p? This is one of the ones I already said I wish I hadn't. Okay? The p was I had it written down and I've erased it. But if you remember, it's the coefficient of the y prime term, so that's 3x. So your p is equal to minus 3x over x squared, which is minus 3 over x. Would you buy that? Okay, remember when we did the p, we said it's the first, the a sub 1, I think we were calling that of x, divided by a sub 2 of x. Remember? When we wrote this into our standard form, we divided everything by x squared. So it gave us y double prime minus 3 over x y prime. What's that? Yeah, that's how we got our p. It was a coefficient here when we divided by this. So that's minus 3 over x. Okay? Now, if that is our p, what we want to do is integrate minus 3 over x dx. Okay? What would that be? Log x minus 3 log x. Shock! Which would be log of 1 over x cubed. Wouldn't it? Okay? Now, what's the next thing we do to it? Let's see, I put the minus in there. I hope I wanted it there. No, that minus was from there. Now we do e to the minus that integral, which would be log 1 over x cubed. Okay? Or let me rewrite that. I hope I'm not getting too wacko here. That's x to the minus 3, right? By that? And if you take this and move it here, right? That was legal, okay? Then this is x cubed. Because the e undoes the log, log undoes the e. So that's just x cubed. So that's what e to the that is. So what we have here, y2 is equal to x squared times the integral of, this thing was x cubed over x to the fourth dx. Well, this is 1 over x, and that is x squared log x. Okay, and somewhere we need some plus c's or something or another, but we're just going to ignore that, okay, I guess, for right now. And that's exactly what our y2 is, okay, without any constants. The general solution then on the interval from 0 to infinity is given by, it's a second order, so you only need 2. Y is equal to c1 x squared, that's your y1, plus c2 x squared log x. Okay, there are your two constants. That's why you didn't need them anywhere else. Okay. Okay, there's that. That finishes, hey team, section 4.2. So homework exercises, try to do as many as you can of odds 1 through 15. Okay? Try to do either 17 or 19 or both. And then take a look at 21. And if you happen to have a computer handy that you want to try doing 23, do it. But I don't think 21 or 23 are in the back. Let me see if they are. This is 4.2, isn't it? Yeah, 4.2. Yeah, only go through 19. Okay. You don't have to, what did I do here, folks? I just messed up. No, I'm fine. Oh. I don't know why I had both of those in here. I did. Okay. So only go through 19. Okay. Let's clear the, are there any questions before I clear the ink here? Okay. 4.3 is dealing with, and we got a few minutes to get going on this, at least 10, 11, 12, something like that. Homogeneous linear equations with constant coefficients. Okay? Remember, we've been sort of generally having coefficients that were some function of x. Now we're going to let them just be constant. So it seems like we're getting a little easier. Thank goodness. Okay? We're ready for that, aren't we? Okay. So as a means, all this motivation, I don't know if I care for it enough. Let's return to the first order differential equations. Homogeneous linear equation would be something like ay prime plus by is equal to 0. Ay prime plus by equals 0. Homogeneous because it's equal to 0, first order, and your constants are now constants, not variables, not functions of x, okay? Now, the only requirement here, a cannot equal 0. Because if a was equal to 0, you'd have by is equal to 0, and that would mean y was always 0. I mean, because b wouldn't always have to be 0. Okay, so a can't be 0. So you do have a differential equation. Okay. And b are constants which could be 0, but generally probably would not be, but it could be. This type of equation can be solved either by separation of variables, which is a fun way to do, or by the aid of an integrating factor, which seems like such a pain in the neck way to go. But there is another solution method, so we want as many solution methods as possible, don't we? That keeps it less confusing, okay? One that uses only algebra. Hey, maybe there is merit here. Before illustrating this alternative method, we make one observation, okay? Let's solve that equation solve that for y prime, okay? So in other words, what we're going to do is subtract the by from both sides, and that gives us a y prime is equal to minus by. Okay with that? Divide both sides by a, and now we have y prime is equal to minus b over a times y. That's not too bad, is it? Okay? Now, they don't like to leave it like that. They just want to call it ky, where k is a constant. Well, a and b were the constants. As long as a is not 0, this could be written as ky. Okay. This observation reveals the nature of the unknown solution, y. The only non-trivial elementary function whose derivative is a constant multiple of itself is what? What is the only function that the derivative of the function is equal to a constant times the same function? Always. E to the ky. Wouldn't it be? Or kx, I would guess we would say. Because if y is equal to e to the kx, what is y prime? Say again? Isn't it? And here we have that y prime is equal to k times y. The only function that will work for, right? Hey, this ain't too bad, is it? Okay? So, this observation reveals that the nature of the unknown solutions of y, the only non-trivial function is derivative of, yeah, we already said that. Now, wait. The only non-trivial elementary function whose derivative is a constant multiple of itself is an exponential function, e to the, and they are now calling it mx, okay? They can call it anything they want to. So the new solution method, if we substitute y is equal to mx, m to the x, y equal e to the mx, then y prime with m e to the mx, into that we then get your solutions. Well, let's do that. This is going, okay. Rather than k's, they're going to m's. Y is equal to e to the mx. There's a reason for this, but it's not clear yet. Okay? Okay? Then y prime is equal to what? M e to the mx, right? Okay? Now, if you have a y prime plus b y is equal to 0, and you plug these in, you get A, M, that means morning, I'm just kidding, e to the mx, plus B, e to the mx is equal to 0. Right? Now guess what? We can factor that, can't we? Factor out a e to the mx. What does it leave us with? Morning plus B is equal to, you smart alecky, is equal to 0. Okay. Now let me ask you a question. Is e to the mx ever equal to 0? Never equal to 0. May approach it and approach it and approach it, but never can be 0. So that means our solution is AM plus B is equal to 0. Guess what B is going to be? I mean, what M is going to be? Subtract B from both sides, and you get morning is equal to minus B. So M is equal to minus B over A. Okay. Did we need that? I guess not. You could have, but okay. So let's try it with some actual numbers. I think we can remember all this easily enough, can't we? Okay. What if we had this? 2y prime plus 5y is equal to 0. Okay. Guess what our polynomial is going to be? If y is equal to e to the mx, right? That's our guess solution, right? What would that be then? Okay, yeah, you don't have to do all that. Let's just do that. 2m plus 5 is equal to 0, right? Isn't that what it's going to wind up being? Okay. You can go and do all that other, but yeah, it's going to wind up that, right? So m is equal to minus 5 over 2. Okay? Okay. So, what does that give us? The solution is y is equal to e to the 5 halves x. Okay? Minus 5 halves x. Okay, sorry. Minus 5 over 2. That's an x. Looks like a y. Okay. X. Okay? That's the solution for all real numbers x's. Okay? So you could also write this y is equal to c1 e to the minus 5 halves x. Okay, that's your general solution. In this section, we will see that the foregoing procedure can produce exponential solutions for homogeneous linear order differential equations if you had this. A sub n, y to the nth derivative of y, plus a sub n minus 1, y to the n minus 1, the nth derivative of y, n minus 1 derivative of y, plus a sub n minus 2, y the n minus second derivative of y, plus dot, 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 all the way down to let's do 2y double prime plus a1 y prime plus a0 y is equal to 0. And if you had that, and every one of the coefficients was not a function of x, but a constant, real number, let's keep them real numbers for a while, real values, positive, negative, fraction, decimal, rational, irrational, it doesn't matter, as long as they're constant, then no, I'm sorry. Right now, we're going to keep them integers. In fact, positive integers, okay, for right now, okay? The coefficients, no, I'm sorry. No, they're real constants. The counters are, of course, 0 to 1, not to n. They're, okay, so they're real numbers. Okay. Yuck. We'll start next time. That was just introduction, and it was a long enough introduction. We'll start next time with 4.3, and frankly, things that I think are going to speed up and be a little more fun. Not that they haven't been fun, but, you know, I think we'll get a little better. Okay? We'll move on from there. Oh, I know where the second page came from. It came from my answers in the back. 4, 2, 4, 3. That's what I was using it for. I wondered where that popped up from right there. Okay. We'll pick up and go from there. We will see you on Wednesday. Remember, my office hours tomorrow are only going to be something like 12:45 to 1:15. And then on Wednesday, you're going to be something like 12 to 1:15. And on Friday, not at all. Okay.
What time do you need today?
About 5:15. Unless I have to go to the Birmingham campus and catch somebody, but I think Mr. Holloway's going to try to do that. But if it winds up he can't get over there, then I got to carry something over there. He said he usually goes, but he can't always guarantee it.
I think you found that. I just went to check to see if he was there for that.
Okay, I'll see you. And even if I'm not in my office, you can slide out. Okay. Actually, this afternoon turned out far better than I thought it might, because my sleep was racked. Let me turn this off. Last night, oh wait, I need to do this first.